Assalamu alaikum, dear students. This is Wajid Ali Shah, and today we are going to start the second stream of online classes for class second year subject physics. Second term includes chapter number 4, 5, 6, and 7. There are 4 chapters which will be covered in this stream of online classes. Today, this is chapter number 4. Let us take a start with chapter number 4. The name of the chapter is Electromagnetic Induction, which is given on page number 146 in class second year textbook board Peshawar KPK. As we can see from the name, electromagnetic induction. In the previous chapter number 3, electromagnetism, we had discussed a concept of electromagnetism which was discovered by Oersted in USA in 1820. Electromagnetism is basically a combination of two concepts, electricity and magnetism. Electromagnetism is defined as the magnetic effect produced by electricity. But here in this chapter number 4, electromagnetic induction, which was discovered by Michael Faraday in 1831 in UK, and simultaneously by another scientist in USA. Same time, same concept, but different locations. Okay. What is electromagnetic induction? Electromagnetic induction. The process in which we can induce electricity by the changing magnetic field is called electromagnetic induction. It is the reverse process of electromagnetism. In electromagnetism, we had discussed the generation of magnetic field with the help of electricity, but here we will discuss the generation of electricity with the help of changing magnetic field. Like in the previous chapter, we had discussed that a static charge, a charge which is at the state of rest, produces only electric field, and a moving charge produces electric as well as magnetic fields, both. Here in this concept, we will be using a changing magnetic field which will induce electricity. Electromagnetic induction was discovered by Michael Faraday, named after him in 1831. He discovered that when the magnetic flux linking a conductor changes, an EMF is induced in the conductor. This phenomenon is known as electromagnetic induction. Here we will study the various aspects of electromagnetic induction. So, let us start with the definition of electromagnetic induction. The process in which a changing magnetic field will induce an electric current or EMF, and because of that EMF, finally current will be induced in a closed loop. Okay, there are so many experiments which we can perform in physics lab to verify the concept. We can also generate electricity in physics lab by the same concept. And majorly, we can see that electricity generated in the whole entire world is being generated by this same concept, which was given by Michael Faraday. The first activity, as this is a concept, so we can explain by performing the experimental arrangement in labs. There are so many activities, so many experiments, so many experimental arrangements which can be used to prove the concept. First one is, let us, activity 1. In this activity, we will take a bar magnet which can easily be available in physics lab. This is north side of the magnet, this is south side of the magnet. A closed coil which consists of so many loops. A galvanometer attached to the loop, which will indicate the presence of induced EMF or induced current. This is a galvanometer G. This is a bar magnet M. And this is a coil C. As we can see that the magnet is so much close to the coil that the magnetic field of this bar magnet will be joining or passing through the loop like this. This is north side of the magnet and this is a coil. Dear students, you must keep in mind that there is no source of energy, no source of current, no source of potential difference applied to this whole circuit, except it is a magnetic field which is passing through the coil. The first point is, when the magnet is in the state of rest, there is no current shown by the galvanometer deflection. It means there is no motion, there is no current or EMF induced in the coil. So, what is the concept? A magnetic field does not induce EMF or current in the circuit, but a changing magnetic field across the coil will be inducing EMF and current into the coil. So let us retake. First part of the experiment is that we can move the bar magnet towards the coil like this. First point is that let us start this north side moving towards the coil. So the magnetic field intensity through this coil will be increased. Simply we can say that magnetic flux will be increasing across the coil. And because of that increasing magnetic flux, we can see a deflection in the galvanometer, which is an indication of the EMF induced in the coil and finally the current induced in the circuit. If in second part of the experiment, if we stop this magnet very close to the coil, when there is no motion of the magnet towards or away from the coil, so again the deflection of galvanometer will be 0. Galvanometer will show no deflection, which is again an indication that when the magnet is so much close to the coil but the magnet is not moving, it means that magnetic flux is not changing. If magnetic flux is not changing, so it means that no induced EMF or no induced current is there in the coil. In third part of the experiment, let us we take this magnet away from the coil. We take it away from the coil. If we start moving the magnet, taking away from the coil, again we can see that the galvanometer needle has been deflected. And because of that deflection, we can conclude that by taking the magnet away from the coil, the magnetic flux across the coil was decreasing, and because of that decreasing flux, again an induced EMF was there in the coil, and finally induced current is also there in the coil. So this time we will see that deflection of the needle of the galvanometer is opposite to the previous case. When the magnet is moving towards the coil, for example, the current is clockwise. If we take the magnet away from the coil, so the current will be anti-clockwise. Direction of motion is reversed, so direction of the current is also reversed. This is a proof, a small activity which we can also perform in physics lab, which can prove that the changing magnetic flux induces EMF or induces the current in the coil. When the magnet comes to the state of rest, no change in magnetic field, even there is a strong magnetic field but not changing. So when the magnetic field is not changing, it means there is no induced EMF or induced current in the coil. Thank you. Have a nice day.